Okay, so electrochemistry, it's basically everything that you have as a toy. You know, your phones, your iPads, your whatever you use, it's electrochemistry. Your car, electrochemistry. Your watches, electrochemistry. It's all electrochemistry. So it's what it's doing, it's creating an electric current by mixing things together. And that process, when you have those different things mixed together, produces an electric current, comes from redox equations. Because in a redox equation, what we're doing is we're swapping electrons. So if we put those two things far apart and put a wire between them, the electrons are going to move from one to the other. So it's a movement of electrons, which comes basically from oxidation reduction reactions. So in order to remember how to do this, we have to remember oxidation numbers. You guys remember all the different rules for oxidation numbers. Okay, this slide presentation is going to go through those steps. But here's an example of zinc and hydrogen, and that's probably hydrochloric acid. And you mix those two together, you're going to get hydrogen gas, and the zinc is going to become a +2 in the zinc. But in order, you got to remember those oxidation numbers. So here's the reaction. One species is oxidized, one species is reduced. Leo, the lion, says grr. So in this one, we start with zinc as a 0. All elements in their native state are going to be 0 oxidation number. Okay? And then when you go through the reaction, if they lose electrons, then they're going to be oxidized. If you have something already starting with a charge, or it may start as a neutral one and it gains electrons, then it's going to be reduced. So going from a +1 to a 0, because this would be the elemental state, H2 is 0, so it's going to gain electrons. Zinc has lost 2 electrons and goes from neutral to a +2, and then the other part is hydrogen has gained those electrons, and it forms hydrogen gas with a 0 charge. So each of those hydrogens in the hydrogen gas have gained an electron. Remember the reducing agent and the oxidizing agent?
Yes.
Okay. So whatever is oxidized is the reducing agent. Whatever is reduced is the oxidizing agent. It's just the opposite from the name of the, whether it's oxidized or reduced. So oxidizing agent, pretty straightforward review. So, assigning oxidation numbers. Here are the rules for assigning oxidation numbers. If it's an elemental form, so if you have just a single metal, or you have one of the Hofbrinkels, they're all going to be 0. Oxidation numbers is 0. If it is an ion, whatever the charge on that ion is going to be the charge that you're going to use for oxidation states. For the most part. There are some exceptions. So if you remember those charges, then you can do this real quickly. Non-metals.
We already learned this.
I know, this is a
We
review.
don't need to go back.
Well, you
No,
wanna
we
just
don't need to go back slides. If we read it, we're good.
You read it, you're good. You want to go on and start balancing a redox equation.
No,
You
what
can
she's
always
saying
go
is
find the
somebody said
video.
Go back a slide, and she said there's no need to go back a slide.
Oh.
I didn't want to go back slide.
Can you please go back one slide for a second?
Okay, sorry.
That's Thank you.
This, by the way, I think is on the handout, is it not?
This is
Yes, it
common.
is.
I just want to write it down so that I can remember.
You have it written down somewhere else, though.
Like it doesn't time.
It's common sense.
I don't care.
Nope, it was not on the handout. But it is in chapter 4. All right?
Go ahead.
So, we're over here to looking at oxidation states in nonmetals, and oxygen is the one we always time assign it a -2. The only time you can't assign it as a -2 is when it's bonded to peroxides, and then the charge works out to be a -1 for that one. Hydrogen, if it's bonded to a metal, is -2. If it's the first element in a formula, it's going to be a positive. Bobby?
I forget, if it's an O2, it has -2 charge, but like,
Well, zero
If it's
to.
O2, it's 0. That goes back to rule number 1. That's the elemental
He
form.
means like if it's CO2.
If it's CO2, then the oxygen will have a -2 charge,
not what I'm looking at.
and then carbon would have a +4, right? CO2?
Yep.
Yep. What did you mean then?
I got it now.
Okay. So, chlorine. Most of the other halogens, I doubt very much if you're ever gonna see a halogen other than a -1. How would you get a halogen with a positive charge?
You have like chlorine on chlorine.
That probably is not gonna happen, but it could be, in a polyatomic ion,
Yeah.
ClO, ClO2, ClO3, the oxygen's gonna be -2, the overall ion is gonna be a -1. So you have to figure out what the chlorine is in there. So there's a positive charge. So in polyatomic ions, we use halogens. They call them anions here. Some of the charges or oxidation numbers in a neutral compound are always 0. The sum of the oxidation numbers in each ion is the neutral charge of the Now, there are a couple of different ways you can balance redox equations. The part that we're going to go through now is called the half reaction method. That's outlined on the handout that I gave you. I'm going to walk through a quick example here. So in the half reaction method, what you're going to do is treat each of the reactions, the oxidation reaction and the reduction reaction as half reactions, balance each of those, then add them together, and that's going to give you your total balanced equation for that overall reaction. And the example we're going to use here, well, not to the example yet. So the first thing you got to do is assign oxidation numbers, figure out what's oxidized, what's reduced. Then you're going to write the half reactions. Then you're going to balance each half reaction, and there are several steps in balancing the half reaction. First part of that is going to be balance all the elements in that half reaction except for hydrogen and oxygen. And now, this is basically the half step for an acid. Bases are slightly different. So after you've got all the elements balanced except for the hydrogen and the oxygen, you're going to add water to balance the oxygen. You're going to add H plus ions to balance the hydrogens out. And then you're going to add electrons on the correct side to balance out the charge. And then when you get through, in some cases you may have to multiply a half reaction, because when you get ready to add those two reactions together, the number of electrons on the left side has got to cancel out the number of electrons on the right side. And you may have to multiply those half reactions by some whole number in order to make that happen, or integer as they say here. And then they'll cancel out and you'll have the final answer. Now we're ready for an example? I'm ready for an example.
I'm ready for
Your
an
PowerPoint
example.
disagrees with you. Oh.
I know, it's just kind of long. How many more points do we have in this PowerPoint? Okay.
Is this the one that came with the book?
It came with this particular
You can
book.
tell.
Okay, here we go. Here's our example. So what we've got is the permanganate ion, MnO4 with a -1 charge. And this is the oxalate ion, anion. And this is the parts of the product, you're gonna end up with manganese with a +2 charge and carbon dioxide. Now, before I go to the next slide, can you guys figure out what's oxidized, what's reduced, and what are the charges for each one of these?
Yes.
Just a little practice.
Yes. Yeah.
Got it?
Yeah.
So what's been oxidized?
Manganese.
Manganese. Because it is gang.
No, sorry.
No.
I got that backwards.
Manganese.
I got that backwards.
Just
I'm
the
sorry.
one, two.
So the number for this one would be, so you got
It'd be
a negative
plus
8,
7.
positive 7, going to a positive 2.
So it's gaining electrons.
So it's gaining electrons, so it's been reduced.
Reduced. It's the oxidizing agent, though.
Yeah. Yes, it is.
The
And
other
then
one's
oxygen?
reducing agent.
Anything happening to oxygen? -2 here, -2 here, -2 there. Nothing's happening there. So it's got to be the carbon. Carbon is going to have, let's see, this is a overall -8. So this is going to have to be what, 3?
3.
It's going to be a +3 here. And then we go over here. This is a -2, so this is going to be a +4. Right?
Yep.
Okay. Got it? All right. So we assign the oxidation numbers, and then define which one's going to be reduced, which one's going to be oxidized. Straightforward.
Why do they not bother putting the charge on oxygen?
Because it's always -2.
Not necessarily.
Unless
It,
it's rock
you know, it depends on the overall reaction, so you have to look at them. And when I was going through that quickly a second ago, I said it was a -2, it's a -2 here, it's a -2 here. So we're not going to worry. You can write them down so you keep it straight, but if it doesn't change, then you don't worry about it.
So like we won't get counted off on the entry test if you write it.
Probably not. Probably not. Because they're wanting to know what's been reduced and what's been oxidized. That's the end result, you know. But if you show that you've done it up here, you know, you're fine, I think. There's always exceptions.
It's a definite maybe.
Yes.
Can you email somebody and find out? Just write down everything you can.
Just go ahead and write it down. You know, if you're concerned, the more information you give them, the better off. So, I mean, just write down -2, -2, -2, and all of them, and you're okay. Okay? And what I would also do, going back to that and thinking about that, now that you asked that question, at this point here, what I would always do is I would match them up just on my own particular thing. I would go like that, and I would look at the numbers. We're going from a +7 to a +2. That means we're gaining electrons. That means we're reduced. So I would put that notation into the problem so that they understand, okay, I know what I'm talking about. I've got some indicators here, and I've got some numbers here, and I'm proving to them that I understand how to do the reactions. Because the more information you provide them to work with, the better grades you'll get. All right, so here's one of the half reactions. Go through the processes. Step 1, you got to balance all the things except for oxygen and hydrogen. Well, I've got 2 carbons here. I need 2 over there. You do that by adding a coefficient in front of the carbon dioxide. Next step, we're going to balance the oxygens. Okay, are our oxygens balanced? They're already balanced because we got 4 here, and now because we put the 2, it's 2 times 2 or 4 over there. So our oxygens are balanced. Do we have any hydrogens to take care of?
Nope.
Okay, so we're done with that one. We go to the second half reaction. We got to balance the metals first. Well, we got 1 magnesium on each side. Now we got to balance the oxygens, and you do that by adding water to the opposite side. So over here, I've got 4 oxygens. I have to put 4 waters to balance that off. Now I've put in hydrogens, so I have to balance those. Are the hydrogens going to go there?
No.
They're going to go over here, because you're going to balance them off. So the next step would be to put the hydrogens in there. And there you go. So 4 times 2 is 8. We have to add 8 protons over here to this side. So that's the addition on this side over here.
Is it
That is
wrong?
really hard to see on here.
Pardon me?
You can You can't see the top one really on this one.
Is it wrong if you add?
You can't see the H2O, but it's there.
Is it wrong
If-
if you add hydrogen in the form of H2? If you like add like 4 H2?
No, you don't, it's always adding in ions, yes, it would be wrong. Because if I put H2 here, that means I got 16 hydrogens over here and it's not balanced.
I mean, like if you put 4 H2.
No, atom is ions.
Okay.
Atom is
Because you also have to
protons.
worry about charges.
Pardon me?
You also have to worry about charges.
Yes, so on this one here, we're gonna have to worry about charges because our charge is not balanced. What's our total charge on this side of the equation over here?
7
You got 8 here,
plus 7.
so it's a +8 and a -1 would be +7. On that side over here,
Plus 2.
we got +2. So there's a difference there
So
of
that means you also need to add 6 electrons. to
Five
this.
electrons.
5
Five
electrons.
electrons.
Yeah, my bad.
7 and 2 would be 5. So that would be the next thing. We're gonna add electrons. We had 5 electrons. Why do we add them to the left side?
Because that's got the bigger.
Because it's more positive.
It's more positive and it has the bigger number, so we want to get that number to match this number over here. If we add them over here, we're going to end up with a -3 charge over here, and we'll still have a +7 over here, so we're not balancing out. We're going to balance those charges out. So we add the electrons to this side. So that gets us this part of the equation. Now, we're going to look at these two equations, and it's going backwards. Okay, so here's the two half reactions that we balanced. And if you look at the two half reactions we balanced, we've got 5 electrons here, 2 electrons over here. And the name of the game is we want all the electrons to disappear when we add them together. So we're going to have to multiply this one by 5 and this one by 2. That will give us 10 electrons here, 10 electrons here. They're going to drop out of the picture, and that also is going to change the coefficients on everything. When you add them together, you'll have all the right coefficients for the complete balanced equation.
So now you have like 16 hydrogens. So many hydrogens.
So, here we go, we're going to add them together after we've multiplied by 2 and 5. And here's the two half reactions after they've been multiplied and added together. It's such a long reaction, they had to put all the reactants here and the products down here. Is there anything else we can do to eliminate things at this particular stage of the game?
Cancel electrons.
Well, so all we can do is cancel electrons.
Yeah.
You know, but you will come up with some examples where you may have water on both sides and you can cancel those out. So you can actually reduce that. So you look at those possible opportunities. And the only thing that appears on both sides, okay, so here's our final reaction. So we got 16 hydrogens on this side. It should be balanced. It should be balanced as far as mass is concerned and balanced as far as charge is concerned. The mass is going to be this times the mass of that, and this times the total mass of this. And the masses will be balanced then. All right?
It doesn't matter what order you write that. Does it?
I don't really think so. I mean, you definitely got to get reactants on one side and products on the
It
other.
don't matter how you
But,
add them together.
Yeah, I don't think so. I don't think there's any particular convention for that. All right, now, also in the handout, I gave you a list of the steps for doing bases. A base is going to be the same thing as the acid, except when you get down to that point, you're going to be adding some things to cancel out all of the hydroxide ions that you have so that you neutralize these. So once the equation is balanced, we've got hydroxides in there. We have to minimize or reduce those. This is where we're going to add some hydrogens, and that's going to create water. So as soon as you have that hydrogen, it's going to bond to the water, or the hydroxide, excuse me, and form water. Now you're probably going to end up with a situation where you're going to have a certain amount of waters on either side. And if you got 5 waters on one side and 3 waters on the other side, well, the 3 is going to cancel out, and you're left with 2 on the first side and nothing on the other side. So you're going to be having waters to cancel out as well as electrons. And this is Roman waters. Okay, so what I want to do now is to give you an opportunity to practice that. So I have a few redox problems I'll put on the board for you to work on.
Oh, my favorite.
We done?
Hold on.